Long before modern heating technology, Native American peoples across North America developed sophisticated shelter designs that kept families comfortable through harsh winters using only passive design principles, local materials, and modest fires. The pit house, built partially below ground level with earthen walls and insulated roof structures, stands out as perhaps the most thermally sophisticated vernacular shelter type developed on the continent. Archaeological evidence documents pit house construction across regions ranging from the Pacific Northwest through the Great Plains, Southwest, and into eastern woodlands, with thousands of identified sites demonstrating the approach's widespread adoption across cultures with limited communication between them. The convergent development suggests that the underlying engineering principles had proven so effective that independent cultures consistently arrived at similar solutions when facing cold winter conditions. Modern research into pit house performance validates the engineering sophistication embedded in these ancient designs, showing that interior conditions remained comfortable with minimal firewood consumption throughout winters that would freeze occupants of conventional above-ground structures. Understanding how pit houses worked, what principles they demonstrated, and what lessons they offer for contemporary sustainable construction helps inform modern building science while honoring the remarkable engineering achievements of indigenous builders. The basic construction of pit houses involved excavating a circular or rectangular pit, typically 2 to 5 feet deep into the ground, then building a roof structure over this excavation using available timber and other materials. The excavated floor provided the living surface, with fire hearths typically positioned centrally beneath smoke holes in the roof. Wall construction varied regionally, with some designs featuring substantial earthen walls built up above the excavation, while others relied primarily on the roof structure for enclosure. The characteristic partial subterranean configuration provided the thermal advantages that distinguished pit houses from fully above-ground alternatives. The entry typically involved a ramp or ladder descending into the pit, often protected from weather by an enclosed entry vestibule. The thermal principles that made pit houses effective involved multiple coordinated mechanisms. The earth surrounding the lower walls provided substantial thermal mass that remained at relatively stable temperatures throughout seasonal cycles. The ground temperature at typical pit depths of 3 to 5 feet remains within 10 to 15 degrees of annual average air temperature year-round, dramatically moderating the extreme seasonal variations that affect above-ground structures. The insulated roof structure prevented heat loss upward through the typically well-insulated assembly. The restricted entry through vestibules or narrow passages minimized air infiltration losses that plague larger openings. The combined thermal management created interior conditions remarkably stable compared to outdoor extremes. The specific temperature performance documented through archaeological experiments and contemporary reconstructions demonstrates the effectiveness of pit house thermal design. Interior temperatures typically stabilized within 20 to 40 degrees of comfortable conditions during cold winter weather without any heat input, requiring only small fires to bring interiors to fully comfortable temperatures even during the coldest periods. The thermal mass of surrounding Earth buffered temperature variations dramatically, with interior temperatures changing by only 5 to 10 degrees across daily cycles, even when outdoor temperatures varied by 40 to 60 degrees. The stable thermal conditions provided sleeping comfort without requiring continuous fire tending throughout nights. Dr. Shoshana Running Elk, an archaeological researcher specializing in indigenous architectural traditions across the American Great Plains, has documented thermal performance data from reconstructed pit houses at research sites in North Dakota and Montana. Her measurements taken during winters with temperatures reaching -30 degrees show that unheated pit house interiors maintain temperatures of 20 to 35 degrees, despite the extreme outdoor conditions. a modest fire consuming less than 5 pounds of firewood per hour raised interior temperatures to 60 to 70 degrees comfortably with thermal mass, retaining this warmth for extended periods after fires burn down. The documented performance validates historical accounts of pit house livability during harsh winter conditions. The regional variations in pit house design reflected local climate conditions, available materials, and cultural preferences while maintaining core thermal principles. Pacific Northwest variants built substantial plank-walled structures with partially excavated floors, combining extensive timber construction with earth contact cooling for summer and heating for winter. Great Plains variants emphasized heavy earthen wall construction, providing substantial thermal mass alongside pit excavation for wind protection. Southwest pit houses often featured flat timber and mud roofs supported by substantial interior posts, with designs evolving gradually into the above-ground Pueblo architecture that later replaced purely subterranean construction in those regions. Eastern Woodlands variants incorporated bark wall coverings and pitched roof configurations suited to regional materials and preferences. The cultural significance of pit houses extended beyond their thermal function into broader aspects of indigenous life organization. The circular or ceremonial configurations of some pit houses reflected spiritual beliefs about relationships between humans, earth, and cosmos. Extended family groups typically shared single pit house structures, with social organization matching the architectural capacity for group dwelling. Seasonal occupation patterns varied regionally, with some peoples using pit houses only during winter months while maintaining different shelter types for warmer seasons. The architectural choices reflected integrated cultural approaches to dwelling rather than purely utilitarian shelter considerations. Nathaniel Firedancer, a cultural preservation specialist working with multiple Plains tribes, to document traditional architectural knowledge, has collected oral history accounts of pit house construction methods and occupation patterns from elder community members. His documented interviews preserve knowledge that written records often missed, while providing insights into the practical realities of daily life within these structures. The preserved knowledge supplements archaeological evidence to produce more complete understanding of how these structures actually functioned in their original contexts. The work contributes to cultural preservation alongside scientific understanding of vernacular architecture traditions. The building science research examining pit house performance has expanded considerably since the 1990s, with multiple universities and research programs conducting both archaeological excavations and reconstruction experiments. The combined investigations produce quantitative data about thermal performance, fuel efficiency, indoor air quality, and other parameters that complement the qualitative cultural documentation. The research demonstrates that indigenous builders understood construction and thermal principles at sophisticated levels despite operating without modern scientific frameworks. The findings challenge historical assumptions about traditional construction as primitive or inferior compared to later construction traditions. The practical construction advantages of pit houses made them accessible to peoples with limited specialized tools and materials. The excavation work required only digging tools and sufficient labor, available to any cooperative community. The roof construction used locally available timber and plant materials without requiring manufactured components. The earth wall construction similarly used abundant local materials without external dependencies. The overall construction process involved primarily manual labor investment over moderate time periods rather than specialized skills or scarce materials. These accessibility characteristics contributed to widespread adoption across diverse cultural and material contexts. Now, for the obstacles and limitations that affect pit house applications in contemporary contexts. First, the seasonal occupation patterns that pit houses traditionally supported fit poorly with contemporary year-round dwelling expectations. The partially subterranean configuration provides excellent winter performance, but can feel confined and damp during warmer seasons when natural ventilation matters more than thermal mass. Traditional occupation patterns often involved moving between pit house winter shelters and different summer structures, an approach incompatible with modern permanent dwelling assumptions. Second, the drainage and moisture management challenges in pit structures require careful attention. Subgrade structures face potential water infiltration from groundwater and surface water flows that above-ground structures can more easily shed. Historical pit houses addressed these challenges through careful site selection, drainage features, and occupancy patterns that allowed some moisture accumulation. Contemporary applications with modern expectations for dry interior conditions require sophisticated waterproofing that adds complexity and cost beyond simple traditional construction. Third, the ventilation challenges in pit structures affected indoor air quality, particularly when cooking or heating fires operated inside the enclosed spaces. Traditional designs included smoke holes and entry ventilation that provided adequate air exchange for typical occupancy levels and fire operations, but the air quality conditions would not meet contemporary expectations. Modernized applications need improved ventilation system design to provide healthy indoor air quality while maintaining the thermal advantages of partially subterranean configuration. Fourth, the regulatory approval challenges for non-standard residential construction complicate contemporary pit house applications. Most building codes assume conventional above-ground residential construction with specific structural, electrical, plumbing, and life safety requirements that pit house configurations may not straightforwardly satisfy. Code compliance for contemporary pit house construction requires creative engineering, custom approvals from local authorities, or building department flexibility that varies substantially across jurisdictions. Fifth, the social acceptance challenges for non-standard housing affect financing, insurance, and resale value considerations that matter for contemporary homeowners. Lenders, insurers, and real estate markets evaluate properties based on conformance with conventional expectations, potentially disadvantaging innovative or traditional alternative construction. These social acceptance factors create practical barriers that may exceed the technical construction challenges for contemporary builders interested in pit house approaches. Despite these contemporary challenges, the principles embedded in pit house design continue, informing modern sustainable construction through applications like earth-sheltered homes, berm-ed construction, and passive thermal mass designs that borrow selectively from indigenous precedents. The specific lessons from pit house design that apply most directly to contemporary construction include the value of earth contact thermal coupling, the importance of thermal mass for stabilizing indoor conditions, the effectiveness of restricted ventilation with vestibules rather than large direct openings, and the integration of structure with site rather than imposing construction on landscape. These principles inform contemporary earth-sheltered house design, super-insulated construction approaches, and passive solar design traditions that achieve substantial performance improvements over conventional construction. Ramon Ironcloud, an architect specializing in contemporary adaptations of indigenous building traditions for residential applications across the American West, has designed multiple homes incorporating pit house thermal principles alongside modern construction methods. His projects feature partially excavated living areas with substantial earth contact for thermal stabilization, traditional-inspired roof forms integrating modern insulation with heritage aesthetics, and entry vestibules providing modern functional equivalents of traditional thermal buffers. The designs demonstrate how traditional principles translate into contemporary contexts, producing buildings that honor heritage while meeting modern performance expectations. The environmental implications of partially subterranean construction approaches that derive from pit house principles prove notably favorable compared to conventional above-ground construction. The reduced energy consumption for heating and cooling across building operational lifespans produces substantial environmental benefits. The use of excavated earth as structural and thermal material reduces embedded energy in construction compared to manufactured components. The durability of earth contact construction exceeds typical above-ground building lifespans, spreading construction impacts across longer operational periods. The environmental characteristics align well with contemporary sustainability concerns, while drawing from traditional knowledge developed across centuries of practical experience. The contemporary research into passive survivability, examining how buildings perform during utility outages and extreme weather events, reveals that earth-coupled designs derived from pit house principles maintain habitable conditions during disruptions that render conventional buildings uninhabitable. The thermal mass and reduced envelope exposure that partially subterranean construction provides buffers indoor conditions against exterior extremes even when mechanical systems fail. The resilience characteristics matter increasingly as climate change produces more frequent extreme weather events that stress infrastructure and building systems. The traditional principles prove relevant to contemporary resilience challenges in ways that indigenous builders probably could not have anticipated. Dr. Thandiwe Mthembu, a building resilience researcher examining climate adaptation strategies for residential buildings, has documented how earth-sheltered construction approaches inspired by indigenous precedents provide exceptional resilience against heat waves that will become more frequent with climate change. Her simulations show that earth-coupled designs maintain habitable interior temperatures during week-long power outages, during extreme heat events that render above-ground buildings dangerously hot. The resilience advantages represent quality-of-life protections that become increasingly valuable as climate conditions intensify. The research frames indigenous building traditions as relevant ancestors of contemporary climate-adapted construction rather than historical curiosities. The psychological and spiritual dimensions of earth-coupled dwelling that pit houses exemplified resonate with contemporary interest in biophilic design and connection to natural systems. The direct contact with earth, the sheltering enclosure of underground spaces, and the integration with landscape rather than imposition on it all produce dwelling experiences that modern occupants often find profoundly satisfying. The psychological benefits complement the practical thermal advantages, creating dwellings that serve human needs holistically rather than narrowly addressing mechanical comfort alone. These qualitative benefits matter to occupants in ways that pure performance metrics cannot fully capture. The smoke management systems embedded in pit house design solve the challenging problem of providing indoor fires while maintaining acceptable air quality for extended occupancy periods. The smoke holes positioned above central hearths allowed hot combustion gases to rise and exit efficiently when fires burned briskly. The roof configuration created draft patterns that pulled smoke upward rather than allowing it to accumulate in occupied spaces. The fire management practices emphasized hot-burning fires that produced minimal smoke rather than smoldering fires that would impair indoor air quality. The integration of structural and operational elements produced reasonably livable conditions despite the challenges of indoor combustion, though by contemporary standards, the air quality would fall short of expectations. Catherine Hayward Bluewater, an archaeologist specializing in indigenous engineering traditions across North American vernacular architecture, has documented how pit house builders incorporated subtle engineering details that reflect sophisticated understanding of airflow and combustion principles. Her excavation work at sites across the northern plains has revealed features including hearth positioning related to predominant wind directions, entry vestibules oriented to avoid drafts across living areas, and roof opening configurations designed for optimal smoke removal. The details demonstrate that pit house construction involved more sophisticated planning than archaeological surveys focused only on obvious structural elements might suggest. The research contributes to growing recognition of the engineering sophistication embedded in indigenous building traditions. The construction process for typical pit houses involved community cooperation that reflected broader indigenous patterns of communal labor on significant projects. Extended family groups and larger community networks collaborated on excavation, timber harvesting, roof construction, and interior outfitting across multi-week construction periods. The cooperative approach distributed labor across the community while building structures that served multi-family occupancy. The social dimensions of construction complemented the architectural outcomes, creating buildings embedded within community fabric rather than built by specialized individual contractors. The cooperative tradition produced dwelling experiences qualitatively different from contemporary construction, where houses become commodities rather than products of community engagement. The long-term occupation patterns at pit house sites revealed through archaeological study demonstrate how individual structures served for substantial time periods before replacement or abandonment. Archaeological layers at major sites show continuous or intermittent occupation across centuries in some cases, with successive generations using structures their ancestors built. The longevity of these earth contact constructions exceeded contemporary building lifespans, in many cases, demonstrating durability that contemporary construction often fails to match. The extended service lives spread construction efforts across multiple generations of benefits, producing favorable lifetime assessments even considering the substantial initial construction effort involved. Consider what pit house traditions teach us about sustainable construction principles. The 4,000-year history of successful pit house construction across diverse cultural and climate contexts demonstrates principles that have proven reliable across time and geography. The thermal performance through passive means dramatically reduces energy consumption for interior comfort without requiring complex mechanical systems. The durable earth contact construction provides building lifespans exceeding those of conventional construction through protection from weather extremes. The use of local materials reduces construction impacts compared to manufactured building components. The integration with landscape respects site conditions rather than fighting them. The resilience during disruptions exceeds that of conventional construction dependent on continuous utility services. The cultural significance honors human relationships with place in ways that contemporary generic construction often neglects. The principles demonstrate that sophisticated engineering can emerge from traditional knowledge refined through generations of practical experience without requiring modern analytical frameworks. The lessons embedded in pit house design apply broadly to contemporary construction challenges, including energy efficiency, climate resilience, construction sustainability, and meaningful dwelling experience. The question isn't whether indigenous building traditions should replace contemporary construction entirely. The question is, what principles from these traditions might inform better approaches to contemporary building challenges? The answers involve recognizing value in earth contact for thermal stability, appreciating thermal mass for indoor condition stabilization, understanding integrated site-building relationships for reduced environmental impact, and respecting traditional knowledge as legitimate engineering achievement worth studying seriously. For anyone interested in sustainable construction, climate resilience, or the intersection between traditional knowledge and contemporary challenges, examining pit house traditions provides valuable perspective informing better thinking about residential construction broadly. The contemporary scholars engaging with indigenous architectural traditions increasingly approach this work as partnership with living indigenous communities rather than as study of past practices by academic outsiders. The partnership approach respects contemporary indigenous expertise, involves community participation in research decisions, and ensures that research benefits indigenous communities alongside academic institutions. The methodological evolution reflects broader recognition that indigenous knowledge traditions remain living intellectual resources rather than fossilized historical artifacts. The research partnerships produce outcomes that honor source communities while advancing broader understanding of vernacular construction principles. Moses Standing Bear, a tribal cultural preservation director leading partnerships between his tribal community and academic research institutions, has emphasized that contemporary engagement with indigenous architectural heritage must center community priorities rather than academic interests. His programs ensure that tribal members participate in research decisions, that research outputs benefit tribal cultural preservation goals, and that commercialization of traditional knowledge remains under community control. The partnership principles he advocates produce more ethical and productive research outcomes than earlier approaches that extracted knowledge from communities without adequate consent or benefit sharing. The frameworks he helps develop inform emerging standards for respectful engagement with indigenous knowledge across multiple fields. The integration of contemporary building science with indigenous construction knowledge produces interesting possibilities for hybrid approaches that honor traditional principles while meeting contemporary performance expectations. Advanced waterproofing materials can address moisture challenges that limited traditional pit house applications. Mechanical ventilation systems can provide indoor air quality exceeding what traditional smoke management achieved. Structural engineering can verify code compliance for partially subterranean configurations. The hybrid approach enables contemporary applications of principles that traditional construction demonstrated effective, expanding the context where these ideas can produce practical benefits. The evolution represents respectful continuation of traditional engineering rather than abandonment or imitation. The hybrid models emerging from these partnerships may offer particularly valuable pathways for sustainable construction in regions where climate challenges demand approaches beyond what conventional construction provides reliably. The educational implications of studying pit house traditions extend beyond historical interest into curricula that could enrich contemporary architecture and engineering education. Traditional design principles offer case studies in integrated systems, thinking that contemporary technical education often handles poorly. The multi-generational refinement of these traditions demonstrates engineering iteration methodologies that complement contemporary analytical approaches. The cultural embedding of construction practices illustrates how buildings serve human communities beyond their mechanical functions. Including indigenous architectural traditions in design education broadens the intellectual resources available to emerging professionals while building appreciation for knowledge traditions that deserve preservation and development.